the intertwining strands of the atom and of electricity. It is time to turn to the third strand, energy. To physicists, the concept of work is that of exerting a force on a body and making it move through some distance. To lift a weight against the pull of gravity is work. To drive a nail into wood against the friction of its fibers is work. Anything capable of performing work is said to possess energy, from Greek words meaning work within. There are various forms of energy. Any moving mass possesses energy by virtue of its motion. That is, a moving hammer will drive a nail into wood, while the same hammer held motionlessly against the nailhead will not do so. Heat is a form of energy, since it will expand steam that will force wheels into motion that can then do work. Electricity, magnetism, sound, and light can be made to perform work and are forms of energy. The forms of energy are so many and so various that scientists were eager to find some rule that covered them all and would therefore serve as a unifying bond. It did not seem impossible that such a rule might exist, since one had been found in connection with matter that appeared in even greater variety than energy did. All matter, whatever its form and shape, possessed mass, and in the 1770s, the French chemist Antoine Laurent Lavoisier, 1743 to 1794, discovered that the quantity of mass was constant if a system of matter were isolated and made to undergo complicated chemical reactions. Everything about it might change, but not its mass. A solid might turn into a gas. However, the English physicist James Prescott Joule, 1818 to 1889, began a series of experiments in which he made use of every form of energy he could think of. In each case, he turned it into heat and allowed the heat to raise the temperature of a given quantity of water. He used the rise in temperature as a measure of the energy. By 1847, he was convinced that any form of energy could be turned into fixed and predictable amounts of heat, that a certain amount of work was equivalent to a certain amount of heat. In that same year, the German physicist Hermann Ludwig Ferdinand von Helmholtz, 1821 to 1894, advanced the general notion that a fixed amount of energy in one form was equal to the same amount of energy in any other form. Energy might change its form over and over, but not change its amount. None could either be destroyed or created. This is the law of conservation of energy. Chemical energy. There is energy in a piece of wood. Left quietly to itself, it seems completely incapable of bringing about any kind of work. Set it on fire, however, and the wood plus the oxygen in the air will give off heat and light that are clearly forms of energy. The heat could help boil water and run a steam engine. The amount of energy in burning wood could be measured if it were mixed with air and allowed to burn in a closed container that was immersed in a known quantity of water. From the rise in temperature of the water, the quantity of energy produced could be measured in units called calories, from a Latin word for heat. The instrument was therefore called a calorimeter. In the 1860s, the French chemist Pierre-Eugène Marcellin Berthelot, 1827 to 1907, carried through hundreds of such determinations. His work, and similar work by others, made it clear that such chemical energy, the energy derived from chemical changes in matter, fits the law of conservation of energy. Here's how it looked in the last decades of the 19th century. Molecules are composed of combinations of atoms. Within the molecules, the atoms stick together more or less tightly. It takes a certain amount of energy to pull a molecule apart into separate atoms against the resistance of the forces holding them together. If, after being pulled apart, the atoms are allowed to come together again, they give off energy. The amount of energy they give off in coming together is exactly equal to the amount of energy that they had to gain before they could separate. This is true of all substances. For instance, hydrogen gas, as it is found on Earth, are always exactly equal. However, the amount of energy involved differs from molecule to molecule. It is quite hard to pull hydrogen molecules apart, and it is even harder to pull oxygen molecules apart. You have to supply about 12% more energy to pull an oxygen molecule apart than to pull a hydrogen molecule apart. Naturally, if you let two oxygen atoms come together to form an oxygen molecule, you get back 12% more energy than if you allow two hydrogen atoms to come together to form a hydrogen molecule. It takes a considerably larger amount of energy to pull apart a water molecule into separate atoms than to pull apart either hydrogen or oxygen molecules. Naturally, that greater energy is also returned once the hydrogen and oxygen atoms are allowed to come back together into water molecules. Next, imagine pulling apart hydrogen and oxygen molecules into hydrogen and oxygen atoms, and then having those atoms come together to form water molecules. A certain amount of energy is put into the system to break up the hydrogen and oxygen molecules, but then a much greater amount of energy is given off when the water molecules form. It is for that reason that a great deal of energy, mostly in the form of heat, is given off if a jet of hydrogen gas and a jet of oxygen gas are allowed to mix